Okay. Yeah, so we'll be mostly doing, we'll be doing group theory. So first is the definition of a group. So mostly we'll just, today we'll go over like the main definitions, just definition of a group and some basic things. And after that we'll try to prove uh, FLT, not the last theorem, we'll prove the Fermat's little theorem using group theory. And then we'll also see some related things. Like there's a more general version of this by group theory, and then we'll see a few related things like partial converses, uniqueness sort of things. So, okay. So this is the definition of a group. So like a group is just a structure where you have this set and you have an operation on the set. So it needs to follow some basic properties like there should be an identity element, which is sort of like your one. So you multiply anything by it and you will get the same thing. Then you have associativity and inverses should exist. So notice that you don't have commutativity. So A star B is not necessarily equal to A star A. So yeah, it can be anything. I think it's just better to look at some examples than you might. Okay, maybe we'll get an idea. It's with an example. So most nice enough structures are groups. So reals are a group under multiplication, right? But you'll have to skip 0. So you take reals, but without 0, and under multiplication. So then you can check that first of all an identity exists because 1 is there and 1 into anything is equal to that thing. And then you have associativity, that's just true. And then inverses exist because you can divide by anything except 0. And then we also have real numbers under addition. And in fact, we don't need this over here. We can do it over R plus also. That's R plus N. Can you think of any other examples? Like just think of any normal sort of multiplication and it will hopefully be a group. Modular. Okay. Yes, complex numbers are a group. Under what are these complex numbers under what? No, naturals under multiplication is not a group because inverses don't exist. Like for 2, you don't have anything. So it's like 2 into that is equal to 1. Yes. Okay, good point. So you have positive rationals multiplication, that is true. Yeah, all of this modulo. What do you mean by modulo? Do you mean real numbers under? Okay. This thing is, it's like matrices or something. No, I'm not sure. I forgot the notation. Okay, matrices, invertible matrices. Yes, FP under. Okay, FP under addition is a group, and FP, not just FP, like Z mod and Z in general is a group under addition. Also, I generally prefer if you can speak up, but this is also where the opposition injective functions with domain of the whole real line. Okay, yeah, that's a great example. But you shouldn't just do injective because you need inverses to exist. You can do bijective functions instead. Yes, exactly. So you need numbers co-prime to n. Okay, that is true. Yeah, that's again a great example. Okay, and in particular, you can do like 0, 1 up to p minus 1. Okay, not 0, sorry. Just these things. Oh my God. Under multiplication, mod p. And yes, for non-commutative things, you have that, like functions. Functions. So you don't need like reals in particular, you can do anything. Surjective with codomain also the whole real life. Yes, bijective. Should be bijective. Okay. So now the point is that this is sort of cheating to give this group separately, because you would know that, okay, you don't need to know, but a primitive root exists modulo p. So it's sort of like, yes, under addition is not necessarily a group. Like it's a group only if n is prime. No, it's a group only if n is prime. But you can't take the set of all coprime numbers. So yeah, these are great examples. Okay, but the point is key a primitive root exists mod p. We know that already. So this set is basically just, if g is the primitive root, then you can think of this as g raised to 1, g raised to 2, and g raised to p minus 1. And then we're just multiplying them, which means we're adding the exponents. So in some sense, it's basically the same as integers modulo p minus 1, because we are taking p minus 1 to be basically the same as 0, because g raised to p minus 1 is congruent to that. So then this thing, we'll say this is how we denote isomorphism, which is a way of saying that it's basically the same. Addition. So yeah, how do we formalize this idea of it being basically the same? Like it's like you take an element and then you just rename it, right? So if you have 1, then you'll just rename it to g, and then if you have 2, you'll rename it to g square and so on. Okay, so this thing, we read it as isomorphism. So then the point is key, this sort of renaming to be basically the same, whatever that means. You need the function, this map, which is taking I to g raised to I. So first of all, it needs to be bijective. F from a set G2, from a group G. Okay, so I should write the whole thing. G comma star. So this is like the group G. The set G combined with its operation is an isomorphism. So first of all, the function, it should be a bijection. And then we want it to behave the same way. So we also have key, if you have two elements, G1 and G2. So then if you first multiply them and then you do this renaming, or if you put G1 and then it should be the same. Okay, so if a function like this exists, this is an isomorphism because it's like they behave the same way after you do this operation. So you can check if all of this is true. then you can say that first of all, we'll need to prove key f of the identity in G is equal to the identity in H. Because I mean, if it's basically the same, then the identity should go to other. So how can we show this?
We said G1 to be the identity, then f of E times G2, which is G2 in D. So f of G2 should be f of G2 times f of the identity, which means f of the identity should be the identity.
Yeah, f of G2 is equal to identity. Okay, this is not the identity necessarily. We have to prove that it's the identity. Yeah, that works exactly. So you just so yeah, in groups in general you can cancel stuff. That's sort of the point of having inverses. So you multiply both of these by the inverse of f of G2 inverse. So then these two will multiply. Okay, so one thing you have to be careful of the order of multiplication. In this case, for inverses, it doesn't matter, but in general. Okay, so this thing just cancels to give the identity because of the way it's defined. And this is also equal to the identity. Yes. And then we know by definition of the identity that this has to be equal to f of each.
Shreyan has a question. When you have something like a group without identity but with inverse?
How would that work? So, okay. If you have inverses, how do you define inverses if you don't have identity?
I think that something like A into A inverse, like the K into B into A inverse is equal to B, right?
A,
But I,
A, okay.
but I think that will imply identity. But maybe we can construct something in which it doesn't imply identity.
Okay, so you're saying the identity is anything such that this holds for all B.
Yeah, right. But no, this is inverse. But maybe you can just have it be identity for some values of p, but not identity for all values of A inverse, right?
No, like this is okay. This is just saying ki AB is equal to B in a normal group, and I'm not sure. Okay, so you keep this axiom, you just don't keep identity. Interesting. Um,
Vairav has a good point though. He says what is A times A inverse equal to?
A times A inverse by definition. Yeah, okay, that is true. It can be, but it's sort of not forcing any. It can be equal to anything, right? If we assume that. Or if we said B equal to A inverse, then I don't know if we get something. Okay, this is interesting. Okay, but then we won't be able to cancel stuff as easily. Right? Can we prove that if AB is equal to AC, then like here we just multiply by A inverse on both sides? Can we prove that if this is true, then B is equal to C?
We can multiply by A inverse on the left side.
Okay, so you multiply by A inverse over here, and
No, I mean, on the other side, AB A inverse equal to AC.
okay, so we do AB inverse, AC inverse. Okay, right. Acha, okay, in that case, if we put B equal to, okay, this is interesting. But then you do have something like A times A inverse is equal to A. So you do have something which multiplies.
But I can just be the identity for the value of A, right? It might not be, it might not work like identity for the value.
Yes, that is true. Okay, so what if we try to set A to be the identity of B? Okay, so if we set A is equal to B inverse.
Are we trying to prove that every group has at most two, every element has exactly one inverse?
Every element has exactly one inverse. Okay, no.
Is that what you're trying to prove?
No, Shreya is asking that instead of keeping these axioms, if we say that we don't have this condition, but we have that for every element, there exists for every A there exists some A inverse such that A inverse is equal to B for all B.
Okay.
But also, by the way, this need not hold for a group. Like this is,
Yes.
if we take the
I-
usual definition, then it means this, which is not necessary.
yes.
Then
What's
won't
the
it
difference?
exist an element such that A times that element is itself? Because
Yeah, that does exist, but
no, so then you
yeah,
can show
but
that
don't
they
know.
come.
That's just like the identity for A specifically. It need not be the identity in general.
Yeah. But somehow, but we should be able to get over that, right? Like, if you have A times C is A and B times C is B, and B times D is B, then we should be able to force that C is equal to D. Like, surely two can't exist.
Yeah, this is true. So we do have, so we are allowed to cancel stuff. Okay, so if it is finite, if the field,
If it is finite, then I'm done. If it is finite, it has an identity. I have symbol for
yeah,
infinity.
I think it should work out if it's finite.
Yeah.
I don't
for
know.
infinity.
Yeah, I'll get back to you after. We'll talk about this after the class. This is interesting. Okay, what's the difference between a group and a field? Okay, so a field has a lot of other stuff. Like a field has a notion of multiplication and a notion of addition. And yeah, like basically all the conditions hold for a field. So they are associative, commutative, distributive law holds. So there are a lot of other things. Groups are a lot simpler. You only have one operation. Okay. So anyway, yeah, this is one thing, and then we were going to prove ki f of g inverse is equal to f of g inverse, and like just to show that it is a true isomorphism. Like they are still basically the same after you do this. The two sets. How can we prove this?
Yes, we just start with what we ended last bar, E of h equals f e of g, and then multiply by f of g inverse on both sides.
Okay. Oh, right. Yes. No, wait, by f of g inverse, like the inverse is
I
outside.
think he means f of g times G inverse.
Okay.
Is it?
Yeah, that works. Also, I might in general skip this star. Like it's just fine. You just write it out like usual multiplication. It's okay. So this thing is equal to f of g times f of g inverse. It's also equal to mm, the identity. Yeah, so then we are done because we can multiply on both sides by this thing. And then let me put this or to move this up. Yes. So now we can multiply by this thing on both sides. And then we'll just get that, first of all, identity multiplied by anything is that same thing. Then we'll directly get that f of g inverse is equal to f of, no, not like this. Inverse g inverse times f of g. So these things cancel, times f of g. So these things both cancel to give identity. And then identity into anything is that. Then we are done. Okay. So you have isomorphisms which are like to show they're basically the same, just renamed a little bit. And more generally, you have homomorphisms, which are functions, again, between groups, like more general functions. So again, if you have a homomorphism f from G to H, we come start. H. So then all this means is that it should respect the operation. We don't care about it being bijective anymore. We just say that for G1 times G2 should be equal to that f of G2. Like most of the things are like that. So for instance, you have a homomorphism from integers under addition to z mod and z, again under addition. And that's just you send every value to its value, you send every number to its value mod n. So if you can,
Yes.
okay, now we can prove the main result, which is that, okay, so this is like a more generalized version of, okay, what is this? Weiler-Stachant R of Fermat's little theorem. No, this is wrong. Sorry about that. Lagrange's theorem, yes. Okay, so first of all, I forgot to mention at the start, if you have a group, then a subgroup is just, yes, okay. That a subgroup is a subset and it's also a group under the same operation. Okay. So this is about the cardinalities of subgroups. So if H is a subgroup of G, now I'll skip the operation, but it's the same operation for both. G, then cardinality of H divides the cardinality of G. So like in the case of Fermat's little theorem, we're just saying that access to P minus 1 is congruent to 0. No, not 0, sorry, 1 mod P. And the point is that P minus 1 is the cardinality of this set of FP, the non-zero values, under of the group under multiplication. So then we are saying that if you take this element and the group generated by it, okay, so with an element you can generate a group like identity x, x square, and so on. So then we know that the size of this group, so this will go on till the order x to the d. And after that, it will just repeat. Okay, not x to the d, x to the d minus 1. So the cardinality of this thing is equal to d. D is equal to. So what it's saying is that d will divide p minus 1. So RD divides p minus 1, and then this is just true. So yeah, more generally, you also have like Fermat's, no, not Fermat's, Euler's theorem. Wait. Which Euler's theorem is this? By which you are done? Like, aren't we just done because of orders? No, I don't see the point of using Euler's theorem. Like, we are proving Fermat's little theorem. So what's the point of citing Euler's theorem over here? Okay. So anyway, yeah, this also works for other things. Like it works for Euler's theorem kx is to phi of n is congruent to 1 for x coprime. So we take x coprime because x is in the group of all coprime of all numbers quotient of all numbers coprime to n. Okay, so now let's try to see the proof of this. So do you have any ideas? How would you prove something like this about the cardinality? Anyway, just like how would you go about proving the result about cardinalities?
Can we try saying having dividing it into that subgroup and copies of that subgroup just shifted?
Yes, that exactly works. So yeah, that is the idea. So like we look at this equivalence relation, which is that A is related to B if A B inverse belongs to H. And then for this thing, choose colors look better. Okay, so first need to prove that it's an equivalence relation, and then we'll see that the classes the equivalence classes which this induces, they are all of size h. So then like G is partitioned into sets of size h. Okay, so first of all, we need to prove symmetry. So for symmetry, we just need to show that if A is equivalent to B, then so we need to show B equivalent to A, which is just saying that B times A inverse should belong to H. But this is true because B times A inverse is the inverse of AB inverse. Like AB inverse is equal to BA inverse. And the way to check this is just that it works. Like it satisfies the usual inverse property. So if you multiply it on the left, then the A inverse and the A will cancel, and then you'll have BB inverse, which is identity. And if you multiply it over here, then these two will cancel. Then it just works out. Also like we will, yeah, I forgot to mention that identity is unique and inverses are unique. That's kind of, yeah, that's fine. Like you can try it on your own later. It's not very hard. Okay. So symmetry is there, and then we need to take multiplicity, I believe. Like whatever, the point is ki A is related to A. So this is just true because A inverse is equal to identity, which belongs to H. Because well, there exists some identity in it, so it has to be that same identity which is in G. And that's just cause like it follows the identity thing. So if you look at okay, so if you take if identity of H was different, then you just square it, which is like identity of H times the identity of H. And this is equal to identity of H because of identity reasons. And then you can just cancel it from both of these sides. And then you look at it as a part of G. So then you can cancel both of these and then you'll get that this thing is equal to the identity in G. Because the operation is the same. The reflexivity holds and transitivity. This is the last thing we need to prove for equivalence relation. A is congruent to B, not congruent. B is equal to C. What do you do? Okay, so it's kind of
We can just say, so,
yeah, go on.
or we can just take the product of whatever they are next, like if AB versus I
Yeah,
and BC versus.
like AB inverse times B times C inverse. And because H is itself a group, we know that this should also belong to H. Because I mean that's a basic property of group key because it's a function, it's a binary operation on that set. If you multiply two elements, then it should remain in the group. So this thing belongs to H and it's just equal to this.
We have some sort of divisibility in cardinality. Like, can we say that this cardinality is divisible by this cardinality for infinite cardinalities?
I don't think so. In fact, I don't know of any examples of one cardinality being larger than the other and not being able to divide it. But I mean, I don't know if any, like it's very hard to imagine some uncountable cardinalities are still fine, but uncountable are just crazy, so it's hard to imagine. So yeah, all of this holds. Now we look at the equivalence classes and all of them will be of size H. So then we'll be done. So if you have an element A, so then we want the set of all for an element A. We want, okay, no, I'll not use A because A is not used usually. G, we'll take G. We want all the things such that G times X inverse belongs to H. And the set of all such X. So this is just saying that G times X inverse. Okay, so it's kind of better to look at the other side. Like it doesn't make any difference. So we'll just look at everything which is related to G. Like all X is that X is related to G. Then what we want is that XG inverse should belong to H. That if XG inverse is equal to H, then X is equal to G times H. So we just have that X. The set of all such X is the set of all G into like G times an element of H. Like the equivalence class of H, but with G times H. This is called a quotient for no particular reason. Like you just take it and you multiply all the elements by G, so then you'll get this. And well, it's just shift by G. So the number of elements should remain the same. Because it's a bijection. Like if you take an element H, if you fix a G, and then if you look at the function which sends X to GH to GH, then this is a bijection. Okay, not a bijection, sorry, this is injective. So the point is that each of these sets, there will be a size H. And then we are just done because you've partitioned G into sets of size H. So then yeah, you can use this for you can use it for Euler's Quotient theorem. You can use it for yeah. I mean, it's just a good thing to know in general. It's also useful for some polynomial stuff sometimes. Like not in Olympiads, but it's nice to know. Okay, so now we have this. Okay, so the one thing which you should look at in general, if you have something like this, is key. Now you've got this set of cosets. Like you've got this equivalent relation. So you've got a set of sets. So I mean, if you see a set, then the natural question to ask is it a group? So this thing is, yeah, unfortunately, it's not quite a group yet. Like you can't think of it as a group as it is. So the usual notion of multiplication would be that if you have two sets, you have a set S1 and you have a set S2, and you're multiplying them. And this is not the Cartesian product. Okay, so this is supposed to be some other set. And like S1 and S2 are both subsets of G. So then you would ideally want to take the set of all S1 times S2, where S1 belongs to S1 and S2 belongs to S2. But sadly, this doesn't work out. So it's not well defined. Like the point is it is well defined. Like the set multiplication is well defined. But if you look at it that way, then it doesn't have inverses, I believe. It doesn't work out. Because like if S1 is equal to G1 times H and S2 is equal to G2 times H, then you need a little bit of extra symmetry to make it work. Like this is not quite symmetric. So then that's the thing. We can't think of this as a group, which is kind of annoying because you want to have as many groups as possible. So then, wait, is everything clear till here? Is the proof of Lagrange's theorem clear?
Yeah.
Okay. Okay, so then we'll look at there is a certain very specific kind of group subgroup for which this sort of set is a group, like the set of all equivalence classes under that equivalence relation. That's called a normal subgroup. Okay, so the condition for normal subgroup is fairly simple. So like here we had this multiplication on the left, right? So we defined GH, just multiplication on the left. So now we can also do multiplication on the right because why not? So then the point is key, we can do we can multiply it on the right also, which can just be the set of H. So if we just insist that GH should be equal to HG for all G, then H is a normal subgroup. Yeah, this is kind of a weird definition for now. The main point is that a normal subgroup can be, okay, so once we define the quotient, then we'll get that we have this set of equivalence classes. Okay, you'll see the motivation for this definition sometime. Okay, so if you look at that quotient set, we denoted by G mod H, where H is a normal subgroup. So then we can just define this sort of multiplication. That if you have G1 times H, and then you have G2 times H, and you want to multiply them. Let's use this sort of multiplication. Okay, let's just not use this multiplication. So then in this case, if it is normal, then you can just directly do it by G1 and G2 and H. So this is also like the pairwise product, because if you have G1 times H, so then that just means it's the set which contains G1. Like it's the equivalence class of G1 and it's the equivalence class of G2. So if you multiply them, you get the equivalence class of G1, G2. So now we need to prove that this is well defined. Like the point is that this was just a matter of representation, right? Here when we chose G1, it could have been anything from that set. Like it could have been any element from the equivalence class, and then this final multiplication should not change. So we need to prove that it's well defined, and then like the other things will follow quite easily. That's where we'll use the fact that it's a normal subgroup. Okay, so all we have to prove is that instead of G1, if we had some other random thing called G1 dash, and G1 prime is such that the set is the same. So that just means that they are equivalent under that equivalence relation. Right, so if you have G1, G2 is that G1 and G1 dash, G1 prime inverse belong to H. Then we should have these two also basically the same. Like here we'll get G1, G2, and then we'll get G1 prime G2. So these should be the same sets. They should the same equivalence class, which is just saying that these two should be equivalent. So then we want G1, G2 times G1 prime G2 inverse. So yeah, I mean, in general, if you want to take inverse of random things, then you just have AB inverse is equal to B inverse A inverse. Because, yeah, I mean, it just works out. If you have this thing, then if you multiply on the right, then you'll get this. These two things will cancel. Then you'll get A inverse, and this is just identity. And then similarly on the right, it works out. So like if we try to do that over here, then first we'll get this inverse, is G2 inverse. And then we have G1 prime inverse. So then this you'll notice just equal to G1 prime inverse, because these two things cancel to give identity. And then you multiply identity, like identity can just be absorbed into the G1, it's fine. Identity doesn't really matter. Yeah, so does this make sense?
Yeah.
Speak of this. Yes, no, something.
Yes, it makes sense.
Okay. So, yeah, then, so now we also have this other group. So we call it like the quotient group G mod H. And yeah, I say mod H because it's like we are modding out by H. So for
It's
instance,
kind of independent. So But H is in a certain sense independent of everything else.
Yeah, exactly. So like, I mean, if you say mod P, so what you're saying is that you're modding out by all the elements which are multiples of P. You just don't care about multiples of P. Right? So that's actually what it is. So if you think of PZ as P times the set of all integers, which is all multiples of P, so then that's all we are doing over here when you think of Z mod PZ. So you take, yeah, it's just like integers under the equivalence relation where two things are the same if the difference belongs in PZ, which is the multiples of. Okay, wait, just give me a second. Oh, sorry about that. Okay.
So is it something like something is a normal subgroup of something else? Then it's Cartesian product, kind of.
Oh, what do you mean by Cartesian product?
Matlab, like H Cartesian product G by H is G. So like something is something is a
Exactly.
normal normal subgroup if and only if you can Cartesian product it to get G.
Yes. Like not exactly, but that is kind of true.
And what is the
Cartesian
not
product,
exactly
you'll have
part?
to do it as a group. But yeah, that's true. I mean, it
Okay.
doesn't make a lot of sense to think of G mod H otherwise, if it's not a normal subgroup, because like it's there, it's a set, but you don't care about random sets too much. It's not a group. So if it's normal, then it becomes a group.
So it's normal if and only if there are two groups, one of which includes it, whose Cartesian product is the other group. Yes, makes sense.
Yes. Yeah, sort of. Okay, yeah. That makes sense. Yes.
I'm not sure if it is the Cartesian product of H and G mod H. If we say G is not commutative, but then we mod it out by something which is, and then we get G mod H is also commutative. So then H cross G mod H will be.
Yeah, but if G is not commutative, then G mod H need not be commutative.
If we take S3, which is in, but then we mod it by a subgroup isomorphic to Z mod 2Z.
Okay.
But the G mod H will become Z mod reset, and but it's not isomorphic here.
I don't get you.
It should not become commutative once you mod it. Okay, wait, I'm not. Yeah, actually, even I'm not sure. What would the isomorphism be if you claim that this is equal to G?
From H comma like if you have H comma GH and multiply by H dash comma G dash H, you will get H dash comma G dash G dash.
No, what's your multiplication? What's your isomorphism?
I have H GH into H dash G dash H is equal to H dash G dash H.
Yeah, that's fine. That's fine. I get how you're doing Cartesian product. I'm just asking you what would your isomorphism be?
No, that is the isomorphism is equal to G, right?
No, but you need to send this to a very specific element.
Oh, okay. Yes, yes. That's what you're saying. So, mm, uh, like we can just say कि GH has has an element which corresponds to the identity element,
Okay.
right?
Yeah, so that's where the problem comes. Ki G is not unique. Like G might depend based on how you're representing. Like you can also have GH is equal to some G prime
Can't you
H.
have multiple isomorphisms?
Yes, but it's not okay. How to do the isomorphism? I think you would have to do them very artificially. Not in a good way. Yes, it is not good. Okay, so if you want to really do
Okay.
the isomorphism, then you will have to do something like take G mod H and then you take the identity element in this.
Yes.
And
The
then
identity element in this will just be H. Is it-
yeah, it's just H. So then you'll have to take the identity element and then send that identity element like by you'll have to artificially send that to the identity in G. And then you'll have to pick some other random thing. I'm not quite sure if it would work.
Don't think it is isomorphic though, so
Yeah.
it shouldn't necessarily be isomorphic.
Can you give an example when you think it will not be isomorphic?
So we take S3,
What is that?
so we write it as well as just permutations on three elements as a group.
Oh, so
So
1, 2, 3,
now,
1, 3.
yes, so now we take the three cycles as a subgroup, H,
Okay.
and now it's actually a normal subgroup.
Is it a normal subgroup? I'm not sure.
Yes, because I guess it has to be because the order of G mod H is just 2. So if something isn't in H, then that times H has to be the same as that at H times that as G as this minus H. So
Uh, and you're claiming this is normal.
yes. And then S3 mod H becomes just so this is a subgroup is abelian and quotient is also abelian, but S3 itself is not abelian, which gives us the contradiction.
Wait, why is it a billion? Why is the quotient is a billion? Okay, yeah, it has two elements, so it must be a billion. Yeah.
But I'm very sure H is um S3 normal.
Okay, so if we try to do that, so let's see.
Because it has half the elements, the if it is in if we take an element G, if it's in H, then of course it's true. If it's not in H, then it'll have to be S3 minus H on both sides, and then we can prove it's normal.
I can't. I don't see how the cyclic group will. What is this cyclic
Say we
group
take
called?
one random element, which is like 1, 2, 3. Cyclic group is just like Z.
Uh,
Basically that only. Okay, so we take 2, 1, 3, and then we multiply it to this. Let's just check what happens. Okay, so 1. Oh my god, do I have to do this by hand? Okay, so nee, this is just identity. So what we want to prove is that that
no, the what is the product of 2, 1, 3 with this will be 2, 1, 3. There will be 1, 3, 2, and then it will be 3, 2, 1.
okay, that's simple enough. 1, 3, 2, and then 3, 2, 1. And from the other side, okay, yeah. Oh right, okay, I see what you mean better. Yes. It's just not equal to this, so it's the other thing. Yeah, true. Okay, so the point is that if we take any other element, then it's either there in H or it's not there in H. If it is there in H, then it will have to belong to the coset of H only. Like if you multiply H by that, then we'll get the same set. And if it's not in H, then we won't get H. So we'll get the other equivalence class. Like this has 6 elements and this has 3. So there's H and there's one other coset. So it's there in one of these, and that just depends on whether G is there in H or not. Okay, so
And-
it is not isomorphic.
So I don't get the argument. So you're saying that S is what? S3 is what is the argument? It's not isomorphic.
Okay, so S3, if you have S3, and then when did you get why it's not there?
You get why it's what?
Why H is not why H is not.
Oh yeah, I get why it's normal.
Yeah, okay, so once you get that, then you want to show that you're claiming that H mod H times G mod H is equivalent, is isomorphic to G. But then since this is a billion and this is a billion, like the product should be a billion. Means committed, like into we should be doing.
Okay. So like is it possible to recover G through H and G by H?
What? Sorry.
Is it possible to recover G through H and G by H?
Okay. Oh yes. Like not directly, I don't think so. Wait, if you're given G by H, then you're actually given the coset. So then you know which one acts as identity. So
No, I mean, you're given something which is you're given something which is isomorphic to G by H, and you're given something which is isomorphic to H. And can you figure out something which is isomorphic to G?
yeah. So then if you're given something which is isomorphic to G mod H, then you have all of those things. Yeah, I don't think that should be true because like it does hold over here. If we are to take in this case, so if we do take the product group and then we quotient it out by H, like if we do take G is equal to this, okay, not G, K. If we take K equal to this and then we take K mod H, then it will be isomorphic to G mod H. Yeah, because you have pairs, no? You have pairs which are like H and GH. And then if you mod it out by these things, then you'll just get sets which are based on the value of this one. Right? So yeah, it will be isomorphic. So no, it's not possible to recover H from just. It's not possible to recover G from H and G by H.
So what else do you need other than H and G by H to recover H? G. Like what are we losing when we divide by a normal subgroup?
Okay, that's a great question. I don't know. I'm not sure.
Okay, to make it, can you at least tell me, given H and G by H, how many possible sets are there which can be divided into H and G by H?
I don't think it doesn't have to be finite, right?
For finite groups, for finite.
For finite groups. Okay, so you have H and you have G by H. Um, maybe it's just all things isomorphic. Okay, I don't know. I'm not sure about that either. So if you have G bar H, and so we know what the H element is. We already have something isomorphic to H. So there's nothing we can do with H. Like H is just useless because if you're given G mod H, then okay, no, we're not given that. Okay, right. So we know that there is some H, and then we have to multiply stuff. I don't know. I'm not sure about that. Okay, also I forgot H and okay. Yeah, I'll get back to you. Sure. We'll talk about this after class. I'm not really sure how to do that. It seems interesting. Okay, by the way, where did we use normal subgroup over here in this proof? Firstly, is the proof complete? That you can mod out by H.
Think so. We also
Okay,
need
this is
to
a
prove
terrible cheat. It is
inverse.
not. Yes. No, what? Okay, yeah, you have to prove inverse. So that for that you can just say ki if you have GH, then you take G inverse H, and then you'll just directly multiply G and G inverse H.
Then I guess we need to prove well-definedness.
Yes. So we only proved one direction of well-definedness. We have one more thing to prove, which is where we'll use the. So like we said ki if we represent this thing in a different way, then we are good. But we still have to do for here. So like if we have another G2 such that G2, if we have another G2 prime such that G2 prime is related to G2, like it's in the same equivalence class, then we need to prove this is saying that G2 times G2 inverse belongs to H. So then what we need to prove is that one second. G1, G2 and is just equal to G1, G2, and then what is it? So this inverse will come out first because the order always swaps. G2 prime inverse, then G1. So here we'll have to use the fact that it's normal. We already know that this thing belongs to H because because we are given that. So then we need to prove that G1H belongs to H. And this is true for all H belonging to H. G.
Is it just kind of saying that basically every multiplication by G and G dash is just shifting H?
Yes. So it's shifting H within the same subgroup, capital H.
So won't you have H products? Like H by G by H has H possible answers?
And wait, please. What? Wait, I'm confused. Which?
G, like H into G by H has H possible answers?
Why is that necessary? Okay, anyways, so like this thing is just saying ki G1 times the whole set H times G1 inverse is as set it's equal to H. And this is just, so you multiply over here by G1 and then you'll get this, which is precisely the normal condition. Yeah. So now let's do a problem, like an actual olympiad-ish problem. So we have a group G. G is a finite group. Group G. H is a subgroup. No, okay, not H. Fine, I'll use N. N is a normal subgroup. Normal subgroup of G. And there exists some H, also subgroup of G. This doesn't have to be normal. And then we have this random looking condition that the cardinality of H. This is sort of like for Lagrange's theorem. Okay, I'll write the statement first. So, this GCD is equal to 1. Prove that. So there is sort of it kind of gives uniqueness for this part for Lagrange's theorem. So like if you have a so in the specific case where G is square free, this is just saying that if you take any subgroup, any two subgroups which have the same cardinality, which are G and N, and one of them is normal, then you'll have this. Then you'll have they are the same group. Because one is contained in the other and cardinality is the same.
So either H is the identity group or H is a subgroup.
Is
So
the
H is a
problem
subgroup
here?
of N. Basically,
Yeah,
it says H is a
like,
aren't we just done by looking at
uh,
the aren't we just done by looking at the what we say factors? We have that on the H absolute value of H divides absolute value of G,
okay.
right? So and absolute value of G is equal to absolute value of G by absolute value of N into absolute value of N.
Yes.
So absolute value of H does not, and we know that either ab absolute value, we know absolute value of H does not divide absolute value of G by N, or H is a
Yeah. Okay,
right,
so we can get cardinality of H divides cardinality of N. Yes.
and we also get that cardinality of H does not divide cardinality of G by N unless H is the no empty subgroup, in which case we are done.
We already know Kiki, this is true. Like cardinality of
Yeah.
G is equal to cardinality of G by cardinality. Yeah, that's
So we have that H is not a subgroup of G by N.
well, H is a subgroup of G. So like the elements of H itself are like their actual values from G. They are not sets. So it doesn't make a lot of sense to say it's not a subgroup of G by N. Like it's not even a subset of G by N. They are just different types of elements. G by N is a set of sets, and this is a set of normal elements. My video looks darker than it should be, but it is over here. It's fine. Okay, so how would you go about proving something like this? It's this.
Okay, we know that whatever H is, since H is co-prime to G by N, can't we say something like it is not why can't we associate a group to G by N? Why can't we associate a subgroup of G to G by N?
Okay. So one thing you can do is you can look at H mod, like the intersection of H and N.
Yeah.
But then I'm not sure if it would remain normal.
It is not normal in the first place.
What do you mean? Like N is normal.
Hmm.
So if you want to mod out by this, okay, wait, why did I put the cardinality? Yeah, if you want to mod out by this, then you need to prove that it's normal. So basically you need to show that if you have H, so looking at this thing, we got to know that this is exactly equivalent to the normal condition. So that's what we'll prove. We'll show that if you have an element of H, then you take an element of H cap N, say it's G, take which one, then it belongs to H cap N. This is all we need to show.
We know this belongs to H. We just have to show that it belongs to N as well.
Exactly. And that is trivial as it happens. Okay, it's not trivial, but it's just direct because like G belongs to N, so and H, well, it belongs to G, so it surely belongs to GL. It belongs to H, so it also belongs to G. And
Yeah.
then we already have this like the normal condition for N just gives this.
I don't get how we get H dash belongs to H.
Okay. So we
Oh,
know,
we're modding out by H. Then you're done. I thought we were modding out by, yeah, there it works.
yeah. Okay, so we can consider this group if you want.
Yes.
And yeah, it is somewhat along this. Like you don't need the group per se, but that's the general intuition.
Because this should be the, what am I saying? What is the word for the group which only contains an identity element and nothing else?
Trivial group.
Okay.
But
So,
it's trivial. Yeah, I mean we have to prove that it's trivial. Yes.
if we look at the prime, the divide, the
Mm.
so the absolute value of this is equal to the absolute value of H divided by absolute value of H intersection N,
Yes.
right?
Hmm.
And that is absolute value of that is div- that div, uh, that is H absolute value of H divided by absolute value of N divides this thing.
Okay, fine. That is true.
Oh, I know there's this issue where we can't just have absolute value of H does not divide absolute value of H.
Wait, what's the issue?
Absolute value of N may not divide absolute value of H.
Yeah, okay, that's fine. No, like you don't care. Divisibility still makes sense in rationals. Okay, so this doesn't, this just belongs to rationals, and you're fine with that.
Oh, divisibility makes sense in rationals.
Like just the same definition works.
Okay. Uh, and we have that this thing is therefore GCT with absolute value of G by absolute value of N is also 0 is 1.
Wait, we prove the other side. Yeah. Like which issue are you talking about? At some point you'll have to stop counting cardinalities and start doing stuff with actual elements. The proof subgroup. Like just, I mean, so if you want to prove subgroup, the only thing you can do
Uh,
is take an element of H and try to prove that it belongs to N. Do something with it and prove that H belongs to N.
why can't we make a group which is of G by H? Why can't we have a subgroup of H which is associated with that group?
We can have this group on this.
No, I'm saying, why can't we have a subgroup of G which works similar to to G by N?
Um, how would you do something like that? There is something similar called like the rank-nullity theorem. It's there in linear algebra, but there you need to do some stuff with basis, and yeah, it's not a good group in that way. Like you don't do stuff with normal
Is the
elements.
conjugate of N union the identity element also a subgroup of G?
One union the identity element. What's the conjugate of n?
The things which are not in M.
So G minus n.
Oh no, that won't work.
Yeah, it won't work. It's not close and then multiplication.
But I guess we look at proof by contrapositive.
Okay.
So then we could suppose H is not a subset of n. So then we get the image of it under the projection map, which takes us to the cosets.
Yes. Yes.
And then the subgroup of that which is inside n,
Hmm.
subgroup of that which is inside n would the quotient of H over that, we could say that is greater than 1,
Hmm.
and then somehow relate it. Because yes, that would be the same as Hn over n something. So that would have caused a that would have proved that it's has degree which has some factor with with the cardinality of G mod n.
Let us
Yeah. The
let us
idea is
assume without loss of generality. Let us assume that N has some element which is not in M,
okay.
right?
Hmm.
So we can just use that element. Can we? Is there a word for growing element? If we have certain element, we just multiply it by itself again and again to just generate a
So
subgroup.
you're taking the group generated by it, fine. So you take EH.
Okay.
So
Yes.
yes.
And this thing will have absolute value dividing the absolute value of G divided by absolute value of N.
Yes, you're right.
And we are done.
Wait, why does it divide G dividing absolute value?
Because this is not in N. There's nothing in N, right?
Okay.
And um, I'm not sure, I just said intuitive if I have to
Yeah, your idea is right, but you need to do some more work. Okay, so what you're sort of doing is proving if what you are saying were to be true. It is not true, fortunately. If that were true, then that would mean that H is itself the trivial group.
Yes, that's what I
Then,
was.
yeah, because then you'll get order divides that. So you need to make it a little bit like it doesn't divide G mod in this way. So if you want to, so yeah, I mean, Bhairav is right in saying
It does divide that, right?
it's divided because like that's how you use the cardinality.
And so it does divide the absolute value of G by absolute value of N, though, I think.
No, not
It
not
doesn't. It doesn't.
no, but it's close, very close. Like you will need to consider H in this set, like the projection of H in this set, and then try to do some basically the same thing, like the same idea. Try to use it in Gmodern.
Oh yeah, you're right. You can just project H onto G by N. We know how to do that. H into N, and we can just generate that thing. And we know that absolute value divides N, and so if it is greater than 1, then we have GCD not equal to 1. So it has to be equal to 1, and so it's the trivial group, and then we are done.
Yeah, okay. So you take H, you take the least case such that H raised to K belongs to N. Is this
Okay.
what you're doing?
I'm taking H which does not belong to N. I am considering N into H, that as the element of G by N.
Hmm.
Okay. I am considering the subgroup generated by that thingy.
Oh yeah, it's this only. So the cardinality of that subgroup is the least case such that H raised to K belongs to N.
Oh, that's the same thing.
Yes, because I mean when you multiply h and
Oh,
with
yes, I got it. Yes, yes, that makes sense.
the square.
Yeah.
Yeah, so then you'll get this k.
Mhm.
And then the point is that k divides cardinality of G mod n. And you can also prove that k divides the cardinality of H. Because
So K must be 0.
not
1. K must be 1.
yeah, it needs to be 1. So it divides the why does it divide the cardinality of H?
Because you are, for every element, we can just do this thing. We can just have h to the k multiplied by it. At h, we can, for any element in h, capital H, we can have h to 0, 1 into that, h to 1 into that, h into the 2 into that, h to k minus 1 into that. Right? So, yeah, same argument as Lagrange.
Everywhere the thing need not be the same.
What do you mean?
Like the value of k need not be the same for all elements of H.
No, I mean for a given h, like for a given lowercase h, we multiply. Let us call it I for sake of easiness of saying. We can have I to the 0 into all elements of h, I to the 1 into all elements of h, I to the 2 into all like we can have an equivalence class.
All of these are equal to H only. Like I into H is equal to H.
Uh,
Because I belongs to H.
exactly. Exactly. Wait, yes. What do we call this subgroup generated by I?
The subgroup generated at which I?
This one, IH1, like an element of H,
You mean
not
the
in
subgroup generated? Okay, so this is the key detail. Do you mean the subgroup generated within H? Like,
Yeah.
will you take?
It is
Okay,
within H by I. What do we call it?
you don't call it anything. Like, you just
Oh,
get a new name for it.
S. Okay. We have S. And we have
Yeah.
K
Okay.
is absolute value of S. Absolute value of S divides H. K divides H.
Yes, K divides S. Why does K divide cardinality of S? Okay, because like
Subgroup.
we'll just go from H to the K and then okay, so if cardinality of S is equal to N, so then you have I to the N is equal to identity. But then if N was not divisible by K, then you can write N is equal to KQ plus R by division algorithm, and then you get KQ times I raised to R. And this thing belongs to N. But this also belongs to N. I raised to KQ belongs to N because I raised to K belongs to N. Right? So
And
this
so I to the R belongs to N, and we have contradiction.
yeah, so I raised to R belongs to N, and then you have a contradiction. So like R has to be equal to 0 because R is definitely less than K and K was the least. Then you have K divides cardinality of S. So then you have and cardinality of S divides cardinality of H because of Lagrange. Because S is a subgroup of H. So yeah, now we just use the GCD argument to get that K is equal to 1. Does this proof make sense?
Yeah.
Yeah, someone other than saying
Yes.
yes. Okay, great. Do you have any other questions, anyone? I think we should end now. We're already over time.
I
So you said you would answer after this. What would you do for that?
Okay, yes. I'll come to you. I'll stop the recording after that. But do you have any other questions about about this stuff?
That's one thing. Can you please just give an example of a group is very weird? A weird finite group.
A weird finite group. I think this set of where was that set? Yes, bijection from S to S can be pretty weird.
No, isn't it just factor of permutation group?
Yeah, the permutation group. That's I believe a very weird group. I mean, if you want something a little bit weirder, you can look at like, okay, so you can take a regular polygon. You can, in general, if you have some random thing, then you can
I mean, by
symmetry.
weird, I mean that because all of these have other properties that you have given. All of the other groups that you have given have very other nice properties. There's something which is not nice other than the fact that it's blue.
Yeah, I mean, this function is sort of the only nice enough non-abelian group. But okay, so there are some other things. There are some other things. Okay.
I mean,
Okay.
permutations are very neat. They have lots of cool stuff in them. So
Yes, that is true. So you can also have like functions. Again, if you take functions, then you can look at the symmetry, like all the degrees of symmetry of any figure. Like you can just take a random figure. Like, say you have a square. Where did it go? Yeah. Okay. Let's say you have a square. So then, what are the various operations which you can do to the square, which will preserve it, like the degrees of the symmetry? So you can rotate it. We can rotate it by 90 degrees. And you can reflect it. Like you can reflect it about this, but that's just okay. Yeah, you can reflect it about this. Reflecting it about this is not anything all new because like it's just rotate and then reflect.
and then 45-degree reflection.
Yes, you can reflect over here. So then you get this function, like you get this group of all the symmetries of it, like all the things which you're allowed to do, and you can compose them like you compose transformations of the plane. Like functions, you just compose them.
Okay.
That's, I believe, the weirdest example.
I, I mean, like, are there some super weird stuff? For example, for normal functions, there's lots of super weird functions which are nowhere continuous, but other, like, is there any super weird thing over here?
Not that much. Wait, well, if you look at infinite groups, though, free groups are a bit.
Oh yeah, yes.
What groups?
The groups. They're just like there's okay. So there are the sort of groups where you, here you just have groups which are generated by a particular element, right? Take an element G and you generate everything.
Yeah.
So it's more general, but over there, over here there was a finite order. Like you go G, G square, G, this the K, and so on. So in free groups, you'll just have okay, so let's say you're given two elements, G and H. So you'll have G, H, G inverse, H inverse, and then you just have all the finite sequences of this. And like
Oh, yeah.
no non-trivial inequalities found. No non-trivial equalities found.
Hmm.
So like something is all you'll do is if you have H inverse, then you'll cancel it. If you have H inverse H, then you'll cancel it, and that's it. That's all you can do.
Hmm. That, so basically, like, words of what with negative number of characters allowed,
Yeah,
basically.
basically yes. And it just works, but it's very weird. So,
Yes, the free group with two elements contains the free group of any other free group on finitely many elements.
Yeah, that makes sense because you can just have you can just have binary representation of the characters.
Yes.
weird. I'll stop the recording and then I'll come to you. How to stop. Stop.
Hmm. Yeah. So